Now we're going to finally go back and show the existence of W star. Um, and we're going to do that in a special case. On this handout, we're going to do this in the special case that W is finite dimensional. So as soon as we restrict to the case where W is finite dimensional, which is pretty much everything we deal with in this class, then we can find a basis for W, which means that W star can be written in terms of that basis. By in terms of, we mean represented as a linear combination of the basis elements. And so we're calling, on the handout, we call that representation X. Now, the handout has this written exactly the right way, but here's a matrix way of representing that might be more familiar of a notation that will help us understand what's going on here. Right here are what we call the normal equations. We find W star because we know that V minus W star is orthogonal to everything that's in W. And so if it's orthogonal to everything that's in W, it's orthogonal to all of the basis vectors of W. Any other vectors would be redundant anyway. And so we write W transpose up here because W transpose will take those basis vectors and make them the rows. And so all those rows times this should be 0. And so these are what we call the normal equations. We'll actually use these in the section below, the least squares problem. So now, here's where we're representing W star. In terms of W, we're calling that representation X. So X is the column that gives us the combination of the columns of W. X shows up on the right. So it's the combination of the columns of W that give us this W star. So if we plug this into the normal equations and rearrange, we get W transpose Wx, that's the W transpose distributed to W star moved over, and equals W transpose V. This is a system of linear equations, and because W is a basis, W transpose W is a nice square matrix invertible. And because this is invertible, then we know that there is a solution. And in fact, that solution is unique.